Hello all. Today I'm going to show us how to manually test this 8-bit DAC, digital to analog converter. The part number is AD7224, made by Analog Devices. Now you can use this procedure as a general foundation to test any DAC that you wish. Now here, according to the block diagram, there's 8 data bit input. That's the digital input. And we have this control circuitry right here. Now all of this is 5-volt compatible. This is your chip select, which is active low, has a bar across the top of it. Right, active low also. Load DAC, which is active low. And reset, also active low. Then you have your power supply and analog output section. Now in our test that we're going to do, I've got it set up for unipolar operation that will go from 0 to 10 volts on the output here. So I have VSS, analog ground, and digital ground all tied to power supply ground. I'll have VDD, the power supply input, at 15 volts DC, and with 1K ohm and 10 volt Zener diode, I'll have the VREF set at 10 volts. And as we change the data bits in from 0 to FF, or 1111, 1111, we will see the output go from 0, thereabouts, up to close to 10 volts on the output. Now, it's not perfect here, so we'll be down in the millivolts when we're at 0, and we won't quite reach 10 volts, but we'll be pretty close to it. Let's take a look at the next page of the data sheet. We'll be using this diagram right here for the pinouts of our IC. Pin 1 is VSS. Pin 4 and 5, 4 is analog ground, 5 is digital ground. We'll be tying 1, 4, and 5 to power supply ground. Pin 2 is the output. That's the analog output of this IC. Pin 3 is VREF. We're going to set that to 10 volts with the 1K ohm resistor and the Zener diode of 10 volts. Now here are the 4 data bits on this side and the 4 data bits on that side. Here's data bit 7, data bit 6, data bit 5, data bit 4, data bit 3, data bit 2, data bit 1, and data bit 0. We're going to be tying those to a dip switch with pull-up resistors. Now here's more of the logic input. Here's your chip select, your write, load DAC, LDAC, and reset. They're all active low. Let's go to the next sheet. Right here. Let's move up and look at the top page here. This right here is the truth table for the logic input. Your reset, load DAC, write, and chip select for the AD7224. We're going to set it up so we don't have to change these. If you tie reset high, load DAC, LDAC low, write low, and chip select low, then both the registers are transparent. And I'll show you in a little bit what these two registers are. But when they're transparent, that means that the data, the 8 bits data, passes through the two registers without needing to control or change the state of any of these. So high on the reset, low on the LDAC, low on the write, and low on the chip select. Low meaning we tie those to power supply ground, and high meaning we tie that to plus 5 volts. Okay, let's go down a little bit. Here, there's an input register. So these are your 8 data bits, and you have an input register. And then that passes through to the DAC register, the digital to analog converter register. You don't have to worry about latching the data into these registers if you tie reset high, chip select low, write low, and load DAC low. The data will pass immediately from the 8 data bits input to the DAC, the digital to analog converter. Now over here is unipolar output operation. From 0 to 10 is what ours is going to be. Let me see if I can back up just a hair so you can see this table down here. This is the unipolar code table. These are the 8 data bits in. So when you have 0, 0, 0, 0, 0, 0, 0, 0 on the 8 data bits in, you have 0 volts on the analog output. When you have all data bits set, 1, 1, 1, 1, 1, 1, 1, 1, then you are at Vref times 255 divided by 256. We're very, very close to 10 volts. And you can see here the circuit diagram for unipolar output operation. Alright, now let me put our circuit back up. Here is our test circuit. These 8 switches right here are going to allow us to change the 8 data bit input from 0 volts or ground up to 5 volts with these pull-up resistors. So when the switch is open, say for instance data bit 0, that switch is open, it has 5 volts on data bit 0 through this pull-up resistor right here. Now this is a 10k ohm resistor. All these are 10k ohm resistors. When I close that switch, data bit 0 sees ground or 0 volts. So open is a 1, closed is a 0. Here's the control inputs right here. We have reset bar tied high to plus 5 volts, LDAC, write, and chip select, all active low, tied to 0 volts or ground. Pin 2 is our analog output. So you want to put your voltmeter or oscilloscope on pin 2 and its ground on power supply ground. Okay, now in the next section we'll talk about the power supply to make all this work. Here we have the power supply circuit that we'll use to power up the digital to analog converter IC and the logic inputs. We have an external power supply set to 15 volts DC that comes in on these binding posts. Positive on the red binding post will go in two different directions. We'll have voltage of 15 volts DC applied to VDD of the digital to analog converter. It will also power up the regulator circuit for the voltage reference. Here we have a 1K ohm resistor, a 10 volt Zener, the part number is 1N4740A, and that is fed into VREF. So we'll have 15 volts here on VDD, 10 volts on VREF. VS, analog ground, or VSS, analog ground, and digital ground are all tied to power supply ground back here. Now the logic inputs require 5 volts. The logic inputs to this IC require a 5 volt signal. So our 8 data bits will be pulled up to 5 volts, and the control signals, the reset bar, will be pulled up to 5 volts. The LDAC, the write, and the chip select, they're all active low. They'll be tied to power supply ground. To make the 5 volts DC for the control input signals, I have a 5 volt regulator, 3 terminal regulator in a TO220 package, filtered with a 1000 microfarad 50 volt electrolytic capacitor, and its output filtered by the 100 microfarad 25 volt electrolytic capacitor. This regulator is taking the 15 volts in and dropping it to 5 volts on the output. So if we were to put our meter from pin 1 to pin 3, we would have 15 volts minus the 5 volts here. We'd have 10 volts dropped across pins 1 and 3 right there. That's the power supply section. Pretty neat, isn't it? That's all right. Okay. Let's go do the test. Today we're going to test the AD7224 digital to analog converter. That's this IC right here. Don't know if you can see it. The wires are in the way. That IC right there. The switches right here are going to be the data bit inputs to that DAC. Over here are the pull-up resistors for that dip switch. And when the switch is on, that input, that data bit input, will be pulled low to ground right here. When the switch is off, the data bit input will be pulled up to 5 volts. Now, the supply voltage here takes 15 volts, but the logic inputs take 5 volts. And what I've got here is the 5-volt regulator that drops the 15 down to 5. So we have 15 coming over here to VDD pin of the DAC, and then the output of the 5-volt regulator is for the pull-up resistors and the logic inputs. Here is the 1K resistor and the 10-volt Zener diode that is making the reference input voltage of pin 3 on that DAC. So let's do the test. Now, right now, the 8 data bits are set to 0. And we have 83 millivolts on the output of the DAC. Here we're going to raise data bit 0 to 5 volts by opening up that switch. And we have 0.119 volts on the output of the DAC, 119 millivolts. Here's data bit 1, raised to plus 5 volts. And we have 0.192 volts on the output of the DAC, pin 2. Here's data bit 2. We have 0.343 volts on the output of the DAC. Data bit 3 going high. 0.648 volts on the output of the DAC. 648 millivolts. Here's data bit 4 going high. We have 1.262 volts on pin 2, the output of the DAC. Data bit 5 going high. We have 2.493 volts on the output. Data bit 6. 4.96 volts on the output of the DAC. Data bit 7. 9.90 volts on the output of the DAC. Let's set everybody to 0 again. The 8 data bits going to 0. We have 83 millivolts on the output of the DAC. Let's set data bit 7 high. That's halfway. We have 5.03 volts on the output of the DAC. That's halfway. Half our reference voltage of 10 volts. Now, I'm the computer here. I'm the one changing the data bits on the input of that DAC to make that output change. So I'm the computer. Here's 1, 2, 3, 4, 5. That's binary 5. 6, binary 7, 8, 9, 10, 11, 12, 13, 14, 15, there's 16. Binary 16 gives us 700 millivolts. 17, 18, 19, 20, 21, 22, 23, 24. Binary 24 gives us 1.004 volts. 25, 26, 27, 28, 29, 30, 31, 32. Binary 32 gives us 1.318. And you can do that all the way up to binary 256 or 255, 0 to 255. That's fascinating, isn't it? Isn't that cool? You don't need a computer to check out a DAC. All you need is some dip switches, power supply section, voltmeter, and a power supply. Is that cool? That is really, really fascinating. That right there is how you manually test a digital to analog converter. Now, in the next video, I'll show you how to set this circuit up to test that DAC in bipolar mode. Right now, we're swinging the output from 0 to 10 volts. But you can have that output go from, say, negative 10 volts to positive 10 volts. Or negative 5 volts to positive 5 volts. Thank you very much for watching. We'll see you next time. Hope you enjoyed that.